We will design a prototype for the expansion board concept called the Reset Vector Board to rid the concept of bugs before building the full iteration 2 machine of the Alt6502. The board provides the possibility to specify the reset vectors by using two dip switches, so that one doesn't have to program the memory positions FFFC and FFFD manually every time you start the computer. Aside from the reset vectors, it will also provide power to the computer and therefore take the 3 power rails 5V and plus/minus 12V as input. The data space in question is very small. It only consists of the two reset vector bytes residing at FFFC and FFFD. The control space is also limited. We will only implement a very small subset of the specification. If you haven't seen the specification episode 4, I suggest you go back and have a look at that. We will skip the identifier, as well as the start and size of the data space, and there is no need for card-specific controls, so only byte 1 is of interest here. To keep things as simple as possible, I will implement byte 1 as a generic read-write word. Since this card cannot generate interrupts, bits 1 to 4 will be don't care. However, by doing this, I can make the card lie to the computer by setting bit 5 to 0. This indicates that there is no data space, while there actually is one. But I don't expect any drivers in any near future to be written for this card, so I think I can get away with that for now. One bit that I will be implementing is the data space active bit. I want to test whether this actually deactivates the address overloading or not, and therefore I need this bit. I want the board to behave nicely on the bus, and therefore the CDD signal must be properly generated, and the board should also respect the card address. So let's have a look at the schematic for this little board. We have the expansion bus connector on the left with all its signals. There are the usual members, the data bus, the address bus, the read-write signal, and CDD and the card address. U9 and U13 are responsible for managing the contents of control register 1, and here are the two switches that sets the value of the reset vector, and these are the buffers driving the contents of the switches to the bus. The chips U1, U2 and U4 makes up the address decoder for both the data space and the control space. It generates signals telling the card to emit the most and least significant bytes of the reset vector, that is, telling the buffers to emit the values of the switches. Another signal out from the address decoder is the control register output enable and write enable. They dictate whether the contents of the data bus shall be written into the control register, or if the contents of the register should be read out to the bus. Finally, we have the CDD signal that goes down to a transistor, pulling the bus CDD signal low. Note that the data space active signal in the control register goes back into the address decoder. If this one goes to 0, it disables the ability to emit the values of the switches to the bus. In order to keep the number of chips small, I made a Steve Wozniak and implemented many of the more complex logical equations by using an EEPROM, just like Steve did when he worked on a cost minimization project at Atari. I wrote a small C program which generates the contents of the EEPROM. So let me give you a quick look or quick overview of the program. First, we have the inputs, and they are listed in an enum here. And we have, for instance, the addresses A0 to A7, and down here we have the read-write signal. And the number of inputs down here is, of course, the number of inputs that we have in the system. And if I add 1, this number of inputs increases by 1. And then we have the output declaration, which is very similar. We have, for instance, the CDD signal here, and we have a similar construction for the number of outputs. And if we go down to the main part of the program, I first determine the size of the logic table, which is the same as the size of the EEPROM. And then I open a file that I should write the contents to later on. And finally, I iterate over the logic table, compute the input for this entry. Then I compute the Boolean value, compute the output from the input, and convert the output back to a binary value and write that value to the file I've opened. And the magic happens in the Boolean transfer function. It contains the logic for the EEPROM. And I've broken down the EEPROM into several lines, several statements that should be relatively easy to read. So first we can take a look at, for instance, the CDD signal. The CDD signal should be true when the data space output enable signal is true, or when the control register output enable is true. And the control register output enable is a few lines above over here, and it is true when the control address is valid and when we have a read operation. And the control address is considered to be valid when the address most significant bits is FF and when the least significant bits are in the control space. And the two underscores here indicate that this is an active low signal, and therefore I need to invert this expression. And this is more or less what we have in the program. Before going into the layout, I'll just mention something about the schematic and layout tools that I use. I currently use KiCad, and that is an open source tool for, obviously, construction of the schematics and layout of the boards. I've used other tools before, like Eagle, and before that, GIDA and PCB, and they all work, but I'm currently very happy with KiCad. In the schematic editor, you have the drawing items on the right, and you may pick a component here. A nice thing is that you don't need to, at this point, to decide which footprint that you want. You just concentrate on the function and the logic. I think this approach handles the two different concerns in a better way. I like that the tool doesn't force you to think about the layout until you actually start working with it. In the layout editor, we have on the far right side all the layers of the board. You may choose which ones to visualize at any time and which one you want to edit. Next to that is a column with options for modifying the layout, like adding tracks, doing copper fill, or draw text or geometric shapes on the board. To the far left we have the options for viewing the PCB, like whether or not to show the copper fill. There are lots of options and settings in this program, but I will use two functions later on. One is showing a 3D version of the board, and the other is to export stuff to manufacturing. So this is the complete schematic of the reset vector board. Now let's have a look at the layout. Unfortunately, I don't have a nice time lapse of this, so we will have to look at it when it's finished. So this is the layout reset vector board. The height is approximately 100 millimeters and the width is about 85 millimeters. So it's not a full-sized expansion board, which can be up to 160 millimeters. So this is just 85 millimeters. On the left side we have the bus connector for the expansion board bus, and on the right side we have the power connector that takes in plus 5 volts and plus minus 12 volts. If we take a look at the copper layers, we can see that on the bottom side we have mostly horizontal connectors, and that's a strategy that I use to make the routing much more easier. If we remove the other stuff here, we can see that most of the lines go this. And if we look at the top side, we see that all those lines are vertically laid out. And this is a strategy to make the layout much easier. It costs a lot of wires, but since I'm going to send off this to PCB production, this is not a major cost for me. If I would have made this in a home environment with etching and drilling the holes, I would have avoided to a much larger extent. So if we put on the layout, after I've done the layout, I do a copper fill to create a ground plane at the bottom, and it's looking pretty good. On the top side, I also do a copper fill to create a plus 5 volt range. They are a little bit broken up, but for this amateurish card with low frequencies and so forth, I don't think this is a major issue. So let's have a look at a 3D generated version of this. I think it looks pretty nice. The components are lined up in straight rows, and the connectors and the silk screen and the component labels seems to be sitting at the same or the correct sides. Both the front side and, as far as I can tell, the back side has its silk screen printed properly. So now it's time to actually send this off to manufacturing, and the first thing that we need to do is to check that the design rules are properly adhered to, and that there's a track width and via diameter and drill diameter and so forth. And now we should run the design rules check program to make sure that the design is actually adhering to these rules. And we have some extra settings for the track width and diameter. And the first thing we can do is to check that we don't have any unconnected stuff, and then we just run the checks, and we have no warnings, so everything is fine. So we can actually proceed and to generate the input files that the manufacturer wants. And this is in KiCad done with the plot menu. And here we should select the Gerber, of course, and then we have the copper layers, the silk screens, and the copper masks and the edge cuts. And those are the layers that my manufacturer wants to have. So just generate the plot, and then we get a number of different files, Gerber files, but it does not include the whole file, so we have to generate a drill file as well. And these settings needs to be checked with your supplier, and these are not actual settings for any supplier. This is just a default setting, but for the sake of showing this, I will generate a drill file of this and compile it and show how to submit this. So a drill file was generated, so let's move on and compile this into a zip file. And for that I have a little helper program. These are the files that are generated and some previous stuff that I had, and there is a program called or a little script I have written called compile C delivery, and it just takes the name for the input and a version and generates a nice zip file and does some consistency checking on the content, so it should be nice to submit. So we'll just run this and specify the name, reset vector board, and the version. In this case I will make up version 13.13. So no warnings, all the layers are included, all the files are included, and we got a nice zip file. So let's move over to the manufacturer's website. Well, this is the zip file, and let's move over to the manufacturer's website. I use seed, but you can use whatever you want. It works for me. I've used it a couple of times for the last PCBs, and actually it has changed a little bit since I was here last. They only supported 4 layers by then, but now they have increased that a little bit. So we can drag and drop this to upload it to the site. So now we have to decide a couple of parameters, like which material that we want to use, how many layers it should be, the dimensions of the board, and so forth. These are a little bit redundant information, but they are provided so that you can see what price this will actually be. And the number of PCBs, it has a minimum of 5, but you can specify quite a few more than this. And then there are some other options like the panelized PCBs and the thickness, and 1.6 is maybe too much for this board, and the color and the surface and so forth. So this is just the stuff that we need to put in, and I know that I won't use these small via holes, and if I would change this to smaller track spacing, the price would go up significantly. And you should be fooled by this $9.9. It is just the basic stuff. Things will add up. There will be shipping, there will be other fees that comes in, so it is quite a bit more, 3 or 4 times more before you're finished. Here you can see the actual board that I submitted, and you can also see that I actually chose the board thickness of 1.2 millimeters, since I thought 1.6 would be a little bit too much. It typically takes 2 weeks for the board to be delivered from China here to clear the customs and whatnot, so it won't be until in episode 7 that we will receive the package and unpack it and see if it actually works as expected or as specified. In the meantime, we will take a look at the mechanics again and actually print and mount some of the pieces all together. See you next time!